Yes, I can't claim to be the owner of this work. I am the self-appointed convener of computational workshops, we called them, in level 2 physics units, PHS. We've heard how evidence-based examples of how to teach, and Russell has given a great motivation of why we should incorporate computing into our teaching. And I was Googling Conrad Wolfram earlier, and I mean, the Wolfram brothers often quote themselves quite often, but he was saying, let's teach as if computers exist. This is the modern world. So I'm just going to talk to you about what we did last year, not so much why. I apologize for the bland slides. We'll get to some juicy ones later. So why did we think it was a good idea? This is unique for me. We had like 6 or 7 lecturers all coming together saying, we want to do this, let's discuss it collaborative. All the level 2 PHS teaching staff said, we want to incorporate computational physics to enhance the learning process. That was the main reason for, regardless of what the students will get out of it, we believed in this. And the reason Russell's already said is that computers can provide visualizations, manipulations that you can't do on a static whiteboard. This doesn't mean the computers are better, it's just a different mode of teaching that we can use to supplement the information we're getting across. And equations written on the board are great, and you can rub them out and change them. On a computer you can do it directly, and you can do things that can't be done by hand. I'll come to that in a moment. And it's there to supplement verbal explanations. So what were the desired learning outcomes? And I actually went back to the planning documents, and this comes from all the lecturers. What do we come up with? We wanted students to know how to set up physics problems on computers that would validate their learning. So these would be things that they could do by hand, maybe inverting a matrix or finding the magnitude of a complex number, something like that, or through other means, could be visual. But we also wanted them to set up problems that couldn't easily be done by hand, including purely numeric solutions and numerical integration of some function, say, and iterative solutions, so loops and things like that. And then this actually comes from Russell. We wanted to endow students with general scientific computing acumen, and so that includes being able to use a computer to do physics, but also to come up with good visualizations of their data. Now, is this a good thing? These are the learning outcomes that we hoped for. Do physics and astronomy students need computational skills? Is there evidence for that? And Russell's already mentioned nationwide push to integrate computing into teaching here in this country. In America, the American Institute of Physics did a survey of 4,000 physics graduates, and they found over half of them were employed in either engineering or IT in the private sector. So it's a big driver for employment. We often hear this from employers that the physicists, in particular physics students, physics astronomy students, have desirable computing skills. And this came up, this is from Scott Findlay, a nice summary he gave of the Science Industry Night, is that several employers were reportedly saying that they want the 3 C's, and I've forgotten what they are. They can collaborate, they can code, and they can communicate. So code is a big part of that. So there's evidence from industry about, and I'm sure the students love to hear these things because they want to get employed at the end of their degree. So what did we do? Well, the Faculty of Science and our school supported the development of 18 2-hour workshops at level 2 across 3 different PHS units, and that was through a unit enhancement grant. So that's how this work was funded. And the bulk of the programming for each of those workshops was done by Dr. Istvan Laszlo, and every single lecturer contributed to that code. Some of them wrote code directly, some of them gave ideas and equations and that sort of thing. And so it was a very collaborative effort. There's a lot of text on these slides. How did we do this? Every fortnight, students sat in a computer lab, and they sat there for 2 hours with a partially completed notebook, writing code, writing equations, and writing textual responses to individual questions that tested the learning outcomes. Some of these notebooks were sparse, and the students had to create a lot of content. Some of them were filled already with graphic visualizations, and you'll see some of those, to give them that wow factor, to say, hey, this is what a computer can do. The textbook questions don't show me this result, but I can actually get a result from the same equations using my computer. Okay, so here's some excerpts from the workshops. This is PHS 2081, and we're looking at using computers to generate pseudo-random numbers to model, say, stochastic motion of electron in a solid in the context of the Drude model. I don't know, so here we have an electron zipping along, and it's drifting due to a force, but it is scattering due to resistance along the way. And here's an example of questions that were given some analytic text equations showing them how you could describe the statistics using a Poisson distribution from the ground up, and then how you could generate random numbers that obey a Poisson distribution that, not just a set of uniform random numbers. Here's another one. This is actually Lincoln Turner's code. This is thermal vibrations in the Ironstein model, a nice toy model looking at random transfers of energies between energy levels. And this is the code that the students were given with instructions. They're given over here some function that was written out, and they had to modify and supplement that with explanatory text, and they were guided through this in the end to create a model that captured internal entities and multiplicities of macrostates, so they could compute, say, in
Mathematica first, or the background to these?
It's built up within each subunit. It's built up from week to week. And did we do enough teaching of Mathematica first? No, we didn't. So we're working on that right now to develop a better introduction to the students.
We started doing it in first year.
Yes.
So this year's students should be better prepared.
Yeah, and that really helps having it in first year. I believe that Mathematica is being used in high school. I think soon. I heard rumours about that. Yes. Actually. Yes, he will, yeah. He'll put it in his next book. I actually skipped over that. I said what we chose as our integrated development environment was Mathematica, and we had a lot of discussion about this. Could have been MATLAB, could have been something else. And I'm calling it an integrated development environment, even though Stephen Wolfram calls it a language. I think we can call it a language, but I don't want to get an argument about Turing completeness and that sort of thing. I think it has worked very well for our needs. Because it incorporates, you can give them a genuine coding experience, but you can also have very high production visualizations at the same time. So here's the calculations of electrostatic potentials. These are exercises over here the students are given. These are just a collection of charges in the electric field from assemblage of charges. Here is just one charge, and we're looking at the field in terms of vectors. And here is me doing an exercise last night. This is the method of images. We've got a metal here with a corner in it, and we've got a point charge out here, and we're trying to find the potential. This is an example of something that a textbook just can't explain to students adequately. And we're moving image charges around, fake charges inside the conductor, and we find that if you're clever enough, you use symmetry, two charges of a different side into the third, placed symmetrically in the corners, will match the appropriate potential energy distribution that solves that problem. Once you've found a single potential, you found the potential, because the result is unique. And that's the method of images. The students actually code parts of this up, but they're also able to use the code itself to do that calculation there. So that's about it for me. That's what we did last year. Did the students like it? We had a mixed bag of set true responses. Anecdotal feedback was good, but I don't want to. The statistics are poor, so we'll see in the long run how we're going with this.
Thank you. Yeah.